Hello, and welcome to Polynomial Functions. Now, a polynomial function f of degree n in the variable x can be represented by this string of characters. F of x, because it's a function, equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. So the powers decrease all the way down to a2 x squared, a1 x plus a sub 0. Now, don't get all sorts of confused. This a sub n is just, instead of calling it a, b, and c for a quadratic, with a polynomial we have no idea what the degree is going to be. So we just go a generic coefficient, a sub n minus 1. It's just the coefficient that goes with x to the power of n minus 1. Each coefficient, a sub k, is a real number. This first one can't be 0, or else we just wouldn't write it, and we'd start as a sub n here. N has to be a non-negative integer. The leading coefficient is a sub n, and the degree is n. All right, so this leading term is going to tell us a lot about the graph. A couple more definitions. Let C be in the domain of f. So we're looking at some value in the domain of f. Then f of c, the y value, the output, is an absolute or global maximum if f of c is greater than or equal to f of x for all x in the domain. This is the key right here, for all x in the domain, like absolutely the highest point. F of c is an absolute minimum if f of c is less than or equal to f of x for all x in the domain. So global is always for all. F of c is a local or relative maximum if it's just the largest near c. All right, near that point, it's the highest. And a local or relative minimum if f of c is the lowest value. So we might have a graph like this. Maybe we'll just stop it right there. And we'll stop it right here. We could see here we have a global max, because that's the highest the graph ever goes. Here we'll have a global minimum, because that's the lowest the graph ever goes. We'll have a relative max. We'll have a relative min, another relative max, and another relative minimum. So in this little area, near that value is the highest one. Near this value is the lowest one. And so that's what we mean by near. And near in math indicates an interval of satisfactory length. And satisfactory length is different depending on how close we want to be. So that's not a set length, so don't get caught on that. That's the part of math that gets a little less rigid, is terms like near. So if I wanted to find local extrema and absolute extrema, I'm going to graph these functions, and I'm going to use a graphing calculator over here. 2x squared, that's not the place to graph it. How about we graph it in y equals 2x squared minus 3x plus 1. If we take a look at the graph, it looks like there's only one turning point, and it looks like there's only one extrema. So maybe we want to zoom in. Let's go to zoom decimal. Zoom decimal is a good window. Zoom decimal allows us to trace in tenths. As we watch the y value, I found a 0, negative 0.8, negative 0.12. So right in here, notice that x equals 0.8, y equals negative 0.12, x equals 0.7, y equals negative 0.12. I'm going to put 0.75. It's a parabola. So we know that let's take a pen here, the absolute minimum is at 3/4 negative 1/8. And you'll find that since this is a parabola, that will be the vertex. All right, we can find the coordinates of the vertex. Let's do our next one. Our next one is negative 3x squared. Until you get into calculus, this will be really the only technique we have for finding absolute and local maximums and minimums. We'll need to see the graph. We'll be able to find the values Again, I used the decimal window so that I could trace. 0.6 is 0.32, 0.7 is 0.33, and then it comes back down again. So I know that my vertex is somewhere around here, my global maximum. In order to calculate it exactly, I can find the maximum, a left bound. So now we're trying to define what that near means for this graph. So somewhere on the left of the highest point, enter. Somewhere on the right of the highest point, enter. And then make a guess somewhere in between, and it'll give us the value of the maximum, and it'll tell you, hey, it's a maximum. Of course, we already selected that, so we knew that was going to be a maximum. This is an absolute max, and it looks like the point is 2/3, 1/3. As we know, those decimal values, the 4s maybe give us pause for concern, but overall, we're good. What about an absolute graph? An absolute value graph, if we go to math, over to number, the absolute value of x plus 3. If we look at the graph, we could see we'll have an absolute minimum. The graph never gets lower. We could expand our window if we needed to, but it looks like we have an absolute minimum. At -3, 0. Fantastic. The last one, let's graph the cube root of x. We could do this in a couple of different ways. If you go to math, you could come down here and get cube root of x. You could also use x to the 1/3 power. Now, cube root of x might not be a graph that you're very familiar with, but no matter how much we zoom out, I'm going to use zoom 6. Notice how this graph seems to always be increasing, like it's increasing from left to right, it keeps going up. There will be no local or absolute extrema. So this happens. Don't find it too odd when you get that answer. All right. Sometimes they just don't have global maximums or minimums. Now, we classify functions in many different ways, and the reason we do this is to kind of categorize them, see if there are any rules that go with all functions of a specific type. Property is function f is even if input of -x has the output the same as positive x. So here is, find the value, a point on the graph where x is, it's looking about 2.5. When x is -2.5, we're at the same height, right? So an input of -x is the same, the output for -x is the same as the output for x. Every single time, always, any 2 points, same distance away from the y-axis. And that's why we say the graph of an even function is symmetric with respect to the y-axis, always. All right, and then we have odd functions, right? With even comes odd. A function f is an odd function if a negative input leads to a negative overall output for every x in the domain. We say this odd function is symmetric with respect to the origin. So I kind of think of it as we're holding this still here at 0, 0. And if we spin it around 180 degrees, we'll get the exact same graph. Hold it still right here at the origin, spin it around 180 degrees, we'll get the same graph. All right, for all three of these. So symmetric with respect to the origin is not a rotational symmetry, but it is the easiest way to visualize it. All right, so functions can be even, functions can be odd, but they can also be neither. Let's back up a minute. That's why I have this on scroll capabilities. I have a little cheater's rule for you. Cheater's rule. All even exponents. By the way, this is not a polynomial. I was just showing examples of even functions. But for polynomials, all even exponents and or constants characterize a function that is considered even. Whereas, another cheater's rule, all odd exponents, no constants. We need everything to be able to change sign in the output, so all odd exponents, because a negative raised to an odd power will give it an opposite response, an add negative output. Determine by graph if the function is even, odd, or neither. So when we look at the graph, we ask ourselves, is this reflected across the y-axis? Not a shifted axis, but the actual y-axis. And you can tell here, no, it's not even. And if we take an input 1, 1, the output will be -1, -1 to be odd. So this one is neither even nor odd. I don't want you to get locked into the it has to be one or the other. Sometimes it can be neither. So to determine algebraically whether the function is even, odd, or neither, we can use our cheater's rule, and we see to the power of 4, to the power of 2, and a constant. I'm going to guess right away that this one's even. But in order to show it, right, when a method is asked for, what we're going to do is we're going to input -x. So everywhere we see an x, we're going to input a -x, and then we're going to simplify. And then we look at this function. This resulting function is exactly the same. This is f of x, and therefore the function is even, because f of -x is the same as f of positive x. All right, so algebraically, we just substitute and simplify. All odd powers, 1 is unwritten exponent, but, so we're thinking odd, f of -x is -x all cubed minus 2 times -x. This is -x cubed plus 2x. Notice if I factor out a negative sign, take the negative out of the x cubed, take a negative out of a positive 2x, and we will have exactly the opposite of the original function, opposite being negative. So this function is odd. One more example. Notice this has a mix of even and odd exponents. As we try to determine if this function is even or odd, little input of -x here. Always algebraically replace x with -x. I always use parentheses so I don't lose that negative sign as I'm raising my powers. Plus x cubed. And I can see that this is not the original function because the sign in the middle is changed. Negative f of x is negative x squared minus x cubed, which would be minus x squared plus x cubed. But there's no minus sign for the x squared, so it is not negative f of x either, so this function is neither even nor odd. Yeah, that's horrible writing. My apologies. And that's it for polynomial functions. Thank you for listening.